Transformers are essential for our everyday life, as without them we wouldn't be able to make benefit of electricity as much as we do. They allow us to increase or reduce the voltage without losing practically any power. This is most useful in power systems, as energy can be transmitted long distances, efficiently. And it is also useful in electronics, where transformers allow us to provide the different circuits within specific desired voltage level. In this video, we will go over the most important parameter concerning electrical transformers. Transformation ratio, magnetic flux, flux leakage and iron cores, copper, eddy currents, hysteresis and various power losses. If you didn't watch our video about the working of inductors, know, it is useful for the understanding of the video. From Faraday-Lenz law we know that a variable magnetic flux is able of inducing a voltage in nearby circuits. When we apply a voltage to a primary winding, a current starts to flow, generating a magnetic flux. As we applied a variable voltage, the magnetic flux is variable too. This magnetic flux is passing through the secondary winding, inducing a voltage. Notice the voltage in both windings is the same. But if we increase the number of turns of the second winding, you can see now its voltage is higher. As the secondary winding is open, there's no current flowing through it. Also, the current flowing through the primary winding is only the magnetizing current. If we now connect a load to the secondary winding, a current will start to flow through it. The secondary winding is providing with energy to the load. But this energy must come from somewhere. Of course, it comes from the primary. But in order to provide with this energy, the current through the primary now has to increase. In ideal transformers, the electrical power in both windings must always be the same. So if we don't change the voltage and the current in the secondary increases, then the current in the primary has to increase too, in order to maintain the power equality condition. If the voltage in the primary is higher than in the secondary, the current in the primary must be lower than the current in the secondary. This is the condition for an equal power in both windings. Transformers encounter a big problem. Let's see what happens with the voltage when one of the coils get far away from each other. Notice the induced voltage in the secondary winding decreases. The reason for this is that when they get far away, the magnetic flux that passes through the secondary winding is reduced, most of the flux gets lost in the air. This doesn't generate power loss, but it's a bit of a waste, as we are not making full use of the machine. The best scenario would be to have some device that directs all the magnetic flux from the primary to the secondary, with no flux wasted in the air, or in the surroundings. If we add a ferromagnetic material between both coils, the magnetic flux will be easily directed from one coil to the other, making full use of the transformer. Of course, a small amount of magnetic flux will be in the air, but it could even be less than the 4% of the total. The reason for this concentration of magnetic field inside the material has to do with the internal structure of ferromagnetic materials. By applying an external magnetic field to the core, we align what we could think are little magnets. This alignment caused all of these small magnetic fields to sum each other, producing a much stronger magnetic field than the original one. But this brought itself a new problem. In order to align all of these small magnetic fields, an extra amount of energy had to be used. This alignment caused friction between particles, and therefore, heat. And every time the magnetic field changes due to the alternating current variation, this small magnetic fields have to be aligned again. Which means, an electrical transformer is losing energy due to this alignments every time the current changes. This is called hysteresis power loss. The higher the frequency of the alternating current, the higher this power loss is. Another loss concerning the metal core is due to the known eddy currents. If a variable magnetic field passes through a conducting material, electric currents in the form of eddies are induced. Of course, these currents generate heat, which means power loss. As with the hysteresis, these eddy current losses also increase with the frequency of the alternating current. An alternative to reducing this power loss is to divide the core into thin, isolated plates. By doing this, we reduce the path for the eddy currents by maintaining the magnetic properties of the material. This means we increase the electrical resistance of the core. Another thing we can do is use a material with a higher electrical resistivity. By doing this, we don't need to divide the core into thin plates, which requires of a lot of hard work. But high resistivity materials, generally, have a lower thermal conductivity, which means the core won't be able to dissipate the heat quickly. Both power losses mentioned before, hysteresis and eddy current, happen all the time the primary winding is connected to a power source. No matter if we have the secondary connected to a load, our transformer will be consuming energy. Of course this energy is not that high, but for a power transformer which can be connected every single day for a whole year, the total energy consumed is significant. For typical power transformers, the heat generated due to core losses can be compared to the heat generated by 10 heaters connected at the same time. The hysteresis and eddy currents power losses depends on the square of the RMS value of the voltage. But generally, this value remains constant, so these power losses are constant. The area under the power versus time graph is the energy. The power is not that high, but notice that if the transformer is connected for a long time the energy loss is important. But transformers also lose power in the windings, known as joule power losses. As a difference with the core, this winding losses are not present when the secondary winding is not connected. But when we connect the transformer to a load, the current in the winding starts to increase, generating heat as a result. If we demand more power from the transformer, this losses will increase significantly. This loss is the sum of the power losses in both the primary and the secondary winding. The Joule effect power loss depends on the square of the current RMS value. Notice it increases significantly if the load we connect requires of a lot of current. There are many types of transformers, the most used are single-phase, three-phase and auto transformers. If you want more videos like this, just leave a comment, subscribe and hit the like button. Thanks for watching.